Let's look at problem 3. Our job is to compare the function g of x equaling f of x plus 2 to the function f of x equals x squared. This can be a little bit of a confusing statement. So the idea here is we have a function f of x equals x squared, and we have another function which is defined by the original function but by adding 2 to every x value. So let's see graphically what this is going to look like. If this is our function x squared, let's just do a quick rudimentary drawing of that. 2, 3, 4. Well, it would look something like here, 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 and then here and here. So this would be a rudimentary drawing of x squared. Okay, so now let's see what happens when I look at this equation. If g of x equals f of x plus 2, and f of x equals x squared, this would equal x plus 2 squared. So g of x is really just x plus 2 squared, but with notation which can disguise the fact a little bit. So if we remember back to our horizontal translation section, this is the same thing as x squared, but just has a horizontal translation to the left. And we know it is a horizontal translation because it is the 2 is modifying the x by adding to it. If it was outside here, we'd have a vertical translation, and if it was right here, we'd have a shift. But since it's right here, we know there is a horizontal translation. So what would this look like? We'd have a point here, we'd have a point here, here, and then it would go up like this a little bit. So this would be a horizontal translation of negative 2. And if you notice here, you can actually see that quite easily in this equation. I shouldn't say easily, but you can actually see it inside this equation when we have f of x plus 2. Once we're adding 2 to the x value of the function, it functions the same way as here. It's quite similar in that the 2 is being added to the x inside the parentheses. Of course, these parentheses don't mean multiplication, they mean a function, but it's quite similar. Now let's look at comparing h of x equals 3 times f of x to f of x equals x squared. Let's just try substituting in f of x. If f of x equals x squared, then I can just put that into f of x and substitute, which would mean that h of x is equal to 3 times x squared. If we were to draw a graph, our red parabola of x squared would look something like this. It doesn't have to be exact, I'm just trying to make a point here. The green one, since it's 3, every point is going to be 3 higher in h of x, so it's going to look really skinny because it has a vertical stretch. So this would be a vertical stretch. If you remember back to our vertical stretches and shrinks, a lot of people identified that it was a vertical stretch, but we have to say it's of 3. I want you to describe to me not only what is happening, but also the quantity. So when we say a vertical stretch of 3, we're saying that the y value at every point has been stretched up by 3. Every time the y value is multiplied by 3, which is why we say it's a vertical stretch of 3. Finally, let's take a look at comparing p of x equals f of x minus 4 to f of x equals x squared. Now let's do the substitution method once again, where we say since f of x equals x squared, then I can replace this f of x with x squared. This would give me p of x is equal to x squared minus 4. If you remember back to your translations unit, this would tell me there is a vertical translation of negative 4. Now if we wanted to draw that really quick, the x squared graph would look something like this. And since we have a minus 4, every y value is 4 less. So that would look something like this for p of x.